The next phase of our integration project is to introduce the fundamental theorem of calculus. This is going to tie our thinking about integration with some mechanical stuff that we did before, specifically derivatives and undoing derivatives, going backwards, antiderivatives. So first we need some notation, because this is a math class and we need notation for things. So we're going to say that the area under the curve, f of x, and above the interval from a to b will be denoted by this symbol. This symbol is going to be the definite integral from a to b of f of x dx. So let's write that out. So we read this symbol by saying the definite integral from a to b of f of x dx. This is how you would speak this symbol. You could switch the two phrases around. You could say the definite integral of f of x dx from a to b. So the of f of x part and the from a to b part are interchangeable. But there's the from a to b of f of x dx. This is just reading it from left to right. This long, tall S symbol says the integral from a to b of f of x dx. The f of x is us evaluating the function. That's going to come from all these f of x's in our discrete sum. The dx is going to be the infinitely small delta x, width of each rectangle. And then the a to b are the values, the boundaries of the interval that we're plugging into the function. So this symbol says the definite integral from a to b of f of x dx. And it will represent the area under the curve f of x and above the interval from a to b. So definite integral notation. I put definite in parentheses because we'll usually just say the integral from a to b of f of x dx. Because once we include that from a to b part, that's what makes this a definite integral. So the from a to b part, this is what makes it a definite integral. So if we're going to say from a to b, we can kind of leave off the definite part because it's very clear that it's a definite integral from a to b. But since we're new, we have to say definite integral. All right. Let's get to the fundamental theorem of calculus portion, because antiderivatives need to show up today. The fundamental theorem of calculus says the following. Let f of x be continuous on the closed interval from a to b. Let's let f of x be continuous on the interval from a to b. Then the definite integral from a to b of f of x dx is equal to. So first we have to stipulate some things. Our function needs to be continuous on a closed interval. Then the definite integral from a to b of f of x dx, that is the area under the curve f of x and above the interval from a to b, is given by the following. Capital F at b minus capital F at a, where capital F is an antiderivative of little f. That is, capital F prime at x is little f at x. And there's our first fundamental theorem of calculus. The integral from a to b of f of x dx is capital F at b minus capital F at a, where capital F is an antiderivative of little f. That is, capital F prime is little f. Pause for copying. I'm not supposed to read that part. One thing to point out here, this is as good a time as any. If you write in all caps, that needs to stop. Math is case sensitive. One of the positive things about the internet is that all caps is now shouting. So that's actually cut down on the number of people that write in all caps. I don't know if that's directly the reason, but it's sure what I'm going with, because I used to have a bunch of students that wrote in all caps. And I was like, oh, are you an architect? And they're like, oh, no. Now I'm like, oh, then knock it off. Math is case sensitive. Capital F, little f. If I just call this one F, then I have to call this one capital F. I have to have different names. Maybe I should just say it more capital. The integral from a to b of f of x dx is f at b minus f at a, but that's terrible. That's a terrible idea. Let's scrap that. We'll just say capital. So this is tying a thing that we're doing, this area under the curve business, with that other thing that we were doing before, derivatives. We just have to do derivatives backwards, and then we can plug in the endpoints. Let's look at an example. Start with a nice straightforward example. Let's suppose that we wanted to integrate from 1 to 2 x squared to x. So what we're going to do is going to find an antiderivative of x squared. We need an antiderivative of x squared. Remember, the process for finding the antiderivative of a function is the inverse of finding the derivative of a function. To find the derivative, we multiply by the exponent, then we subtract 1 from the exponent. The inverse of that is add 1 to the exponent. We add 1 to the exponent and divide by the exponent. Now we need to take this capital F of x and evaluate it at 2 and evaluate it at 1. The way we indicate that we're going to do that is we put a vertical line after the function and say evaluate this from x equals 1 to x equals 2. This notation tells us plug in the 2, plug in the 1, and subtract. So this tells us to do 1/3 2 cubed minus 1/3 1 cubed. So we got 8/3 minus 1/3 is 7/3. Pause for copying because that's a lot of notation. Find the antiderivative and evaluate at the endpoints. We subtract because we're using the Fundamental Theorem of Calculus. Find the antiderivative capital F, evaluate at the endpoints, and then subtract. that is just a mechanical thing that we have to be able to do. Let's look at another example. Because that, by the way, that explanation that I just gave, that we're using the fundamental theorem of calculus, that was essentially me saying because I said so. But I didn't say it in such an aggressive fashion. So don't totally let me off the hook for that one. We're gonna have to build some more around that so it makes more sense. But right now, so you should be like all thanks and then like question mark, because like seriously, that's your explanation. But I appreciate you letting me off the hook with that one. Kind of wave my hands at it. Let's do another example. And see, and let's run this another example, finding an antiderivative, and then plug in the endpoints, just so we can get used to it. So let's suppose we want to integrate from 0 to 4 the function 2x plus 1 dx. So our strategy is to find an antiderivative, then plug in the endpoints. That's the way we're going to phrase this moving forward. That's the way I've said this for a long time, and I'm not going to be able to break that habit. Find the antiderivative, plug in the endpoints. So the antiderivative of 2x plus 1, we've got to do this backwards. We've got to think, what is 2x the derivative of? And 2x is the derivative of x squared. The derivative of x is equal to 1, so the antiderivative of 1 is equal to x. So first we find the antiderivative. And then we plug in the endpoints. So our notation is to write a vertical bar and go from 0 to 4. That means plug in 4, plug in 0, and subtract the results in that order. So we're going to have 4 squared plus 4 minus 0 squared plus 0. So we're going to plug in 4, plug in 0, and subtract. 4 squared is 16, and 4 is 20. Minus 0 is 20. We need to think about what this represents. This definite integral is supposed to represent the area under the line 2x plus 1 and above the interval from 0 to 4. Let's draw a picture and see what that looks like. Here's the line y equals 2x plus 1. And we want this over the interval from 0 to 4. And I want the area under this curve, 2x plus 1, and above the interval from 0 to 4. So I want this area here. So we can see that in this case, the shape is a trapezoid. The area under the line 2x plus 1 forms and above the x-axis, or sorry, above the interval from 0 to 4 forms a trapezoid. If I look at the two heights, the height here is 1, and the height here, 2 times 4 is 8, plus 1 is 9. So the area of the trapezoid is the average of the two heights times the width, or the base, and that's equal to 20. Just like we got from the integral. Any questions? It's important to note that your calculator has this functionality. So what you want to do, I just need the integral parts. What you want to do is go into the math button. This is my favorite button on the calculator because it's a calculator and these are all math buttons, but this one is specifically labeled math. And if you scroll down, you'll see that number 9 is an FNINT. So this is how we calculate an FN integral. I don't know why they have the F. It's like N derivative for numeric derivative, but integral gets FNINT. That's still just numeric integral. So we want to calculate an integral. So we hit enter or just 9. Then we have to get the syntax right. What function? First, we list the function that we're integrating, x squared. Then we make a comma. With respect to what variable? X, that's the dx part. Then we make a comma. And then we say what interval? From 1, comma 2. From 1 to 2, then we close parentheses because we're going to build good habits. And this gives us the 7/3 that we expected. If we wanted it as a fraction, then we could have math and then selected fraction and say, hey, is that a rational number? And the calculator would be like, oh, yeah, it's 7/3. So let's try it on the second one. We press the math button and then the number 9 for numeric integral. We plug in the function 2x plus 1, comma, with respect to x, comma, from 0 to 4. Close parentheses. There's the 20 that we expected. Any questions? Comments?
Mine is actually different on my calculator. I get the little S symbol.
Yes, so the updated TI-84s, instead of having this single line syntax and having to know that, it actually brings up the symbol. So when you hit number 9, it gives you the little integral symbol, and then it has a couple little boxes. So it should have like little boxes down here and a little box up here. If you use the arrow key, doesn't it have like a box for the function too? And then
Yes.
And then a box over here. So
It's
you're still
got
putting
parentheses.
oh, parentheses? Okay.
And the D. Yeah.
So to switch between the 4 different areas, you just press the left and right arrow keys. So I don't have that particular. So if you press left and right, that'll switch you between the boxes. So you would actually do the integral from 0, arrow key 4, arrow key 2x plus 1, arrow key x, and then enter. Any questions? Or comments? Or snide remarks? Aha. In the settings, not in the settings, in the mode, which is the settings button on the calculator. So if this is what it looks like, it starts you off with the from A to B part. So I would just say do the integral from 0 to 4 of 2x plus 1 dx. If you want the single line syntax, because you need to be able to text your answers to your friends and stuff during a test, then the first entry up on top here is math print versus classic. So if you want to go old school, then Math 9 will give you this classic notation. Any questions? Cool. Thanks for bringing that up because I always forget to mention that. And so I usually get an email later on in the day. So I go, hey, my calculator is showing me an integral symbol. I don't know why. I think I'm just never going to remember that this is the updated TIs have this math print version. So there's that. I'm not like opposed to it or anything like that. I just forget. Any questions? Or comments? Or snide remarks? I want to put one last sentence into your subconscious, and that is that the definite integral of a rate of change of a function over an interval gives you the change in the function over that interval. The definite integral of the rate of change of a function over an interval tells you how much the function changed, or let's say gives how much the function changed over that interval. Sometimes how much the function, this is supposed to say much. Sometimes how much the function change is called the total change in the function. The definite integral of the rate of change of a function over an interval gives how much the function changed over that interval. F prime is the rate of change of f. So if we integrate f prime from a to b, we get to know how much the function f changed from a to b. Two x plus 1 is the rate of change of x squared plus x. So the definite integral of this rate of change from 0 to 4 will tell us how much this function has changed from 0 to 4. That's us subtracting. Here's the value of the function at 0. Here's the value of the function at 4. That was an increase of 20. So integrating the rate of change of a function gives you the total change in the function. That's the subtraction business. That's how much the function has changed. If we drive at 60 miles per hour for 4 hours, the change with our distance, our change in position will be 240 miles. That example goes back to our, if the function is constant, we get to multiply to find the area. That's a lot to think about. So I think we should stop there. It's also 1 o'clock, so I think we should stop there. Let's pause the video here and close out today.